Hi, I'm going to do some sample problems today on series circuits and parallel circuits. I'm going to start with series, go through that, and then I'll move into parallel circuits with a different video. So let's start with series circuits. We've got the basic idea of a multi-bulb circuit. So in my schematic mode, instead of the realistic circuits that we see, we're going to have a series circuit look like this. So here's our battery. And when we have a battery like this, the positive terminal is the long one, the negative terminal is the short one. And this is my very fancy way of showing a bulb. So here I've got a battery and a wire connecting it to a bulb, and then a wire connecting that first bulb to the second bulb, wire back to the battery. So we said we needed a complete path of conductors from one end of the battery to the bulb, and then back to the other end of the battery. We've got a complete circuit here. And we call this one in series because it's one after the other. You just have to go through this one to get through this one. And an analogy for resistors in series is the TSA line at the airport. If you've flown anywhere recently, you know that you've got to go through, wait in a long line, then you have to stop and get your passport checked, your ID checked. And after that, you have to wait in a little bit of line and then go through the X-ray machine. So this is like resistors in series, where a resistor slows down the flow, in this case people flow, or electron flow. And so the first person who checks your ID, that's a resistor, and then the second person who's doing the X-ray, that's another resistor, and so it slows everything down. So you've experienced resistors in series if you have gone through the TSA line at the airport recently. So what do we know that's true about a series resistor? Series resistors, R1 and R2. So we saw already that the total resistance in series is just the individual resistors added up. So our total in this case is just going to be R1 plus R2. So if this is 6 ohms and this is 8 ohms, we have a total resistance of 14 ohms. We also have our Ohm's law, which is going to be used in pretty much every circuit question we'll ever do. So this one you will get to see a lot of. So here, Ohm's law, voltage is equal to current times resistance. The voltage is the push of the battery. So what a battery is doing is it's pushing charges around the circuit. So it's just a little pusher. It's like, okay, I'm going to send charges out. You know, a small battery doesn't have a lot of oomph to it. A big battery would send a lot of charges through. So that's the voltage. So this is what the battery provides. And then we've got the resistors, which are the bulbs in our circuit. And then the current, that's the flow. That's how much the charges are flowing. We could have a lot of flow, we could have not much flow. In general, the more flow, the brighter the bulb. So we've got this circuit and we've got this idea for series, and this is true for pretty much everything we're going to be using for our circuits unit. So what do we know about these series circuits? The key pieces are to consider what's true about voltage in a series circuit and what's true about the current in a series circuit. We already have a rule about resistance. So what must be true about current? This is the easy one. Current is just flow. So if you want to think of it as like water flow or people flow, you can do that. So if we have a certain amount of current coming out of this battery, so there's a certain amount of current, we're going to label it I, that comes out of the battery, then, well, there's nowhere for it to go. That same amount of current is going to be going into bulb number 1. Now, when you have current going through a resistor, it doesn't get used up. We don't have charges disappearing. You don't have people disappearing through TSA. Well, you probably do, but you hope they don't. So nothing gets used up by going through a resistor. This is just charges cycling through. So that same current must come out, must go through here, and it's the same current everywhere in a series circuit. So our rule, if you just think about it in terms of flow of charges, the current has to be the same in a series circuit. And one easy way to remember this is the current is the same in a series circuit. So CSSC. Those are all the same letters. Current's the same in a series circuit because where else could the current go? If I have 50 electrons moving per second here, there's 50 here, there's 50 here, there's 50 here. No place for the electrons to go. So that's the rule about current. And that one should be fairly straightforward for people. Most people, that makes sense. The harder part is to consider voltage. So voltage, the battery oomph, I guess we'd call it, how much push there is on the charges in the circuit. So the battery provides a certain voltage, and voltage is always measured across something. So voltage, you don't talk about the voltage at one place, not like you can talk about the current at one place. Voltage is always across an item. So we can talk about the voltage across the battery. And that's the thing where a 9-volt battery has 9 volts across the terminals. Typical AA has 1.5 volts across. So a battery is the source of the movement of the charge, and that voltage is pretty straightforward. I mean, that's just, we've got a 1.5 volt battery, we've got a 9-volt battery, whatever. But we got to think about what is true about the voltage across resistor 1 and what's true about the voltage across resistor 2. So if voltage is like a push, it's an amount that is being pushed on the charges. From here to here, we have a certain amount. Let's say it's 9 volts. So the battery's pushing charges, and it gets to this resistor. So we've got this push of charges, and then we've got all of a sudden something resists the motion of the charges. By the time we get through here, there is less oomph, less push, because we used up a whole bunch of our push getting through this hard resistor. So that means there's less left here. So we use up again more of our push to get through this difficult resistor. And then by the time we're back here, we're got nothing left. And so the voltage in a series circuit has got to all add up to, you can think of it as adding up to balance it out, or you can say it adds up to 0. So we have the voltage across the battery, and that has to be the same as the voltage across R1 plus the voltage across R2. However much push the battery provides is going to be shared between these two. Now, quick question for you. If these two are equal resistors, what do you think is true about how the two resistors share the voltage? So think about that. If they're equally hard, how are they going to compare with the voltage across each of the resistors? If you think, well, they're probably going to share it equally, you're right. So for equal resistors, the voltage is shared equally, but if one of these resistors is more difficult than the other, is harder, it's more resistant, then that resistor is going to need more of the push in order to get those charges through. So if this was a 100 ohm resistor and this was a 20 ohm resistor, well, it should make sense that most of the voltage is going to be used up pushing the charges through this really, really, really hard resistor. It doesn't take as much of the oomph, the push, to get through here, so most of the voltage would end up over here. So the two rules for series circuit problems, the current's the same in a series circuit, and there's your little mnemonic, and then the voltage across the individual components has to add up to the voltage across the battery. So the voltage across the battery has to be equal to the voltage across resistor 1 plus the voltage across resistor 2. These don't have to be the same. So let's see how this would work. The type of questions I'm going to give you are, I'm going to give you just the basic series circuit, all right? I'll give you this picture. We're going to have the voltage across the battery, the voltage across R1. So this is resistor 1, resistor 2, voltage across resistor 2. And I'll give you some pieces of information. So in this case, room here, R1, R2, voltage across the battery, voltage across R1, voltage across R2, and then we'll have the current through the battery, the current through R1, and the current through R2. So you're going to be given a set of numbers. I'll give you some of them, and you have to give me the rest of them. So how do we do this? Well, let's start with, I don't know, let's do this number 3. No, I'm going to do number 2. So I'm going to give you that resistor 2 is 3 ohms. The voltage across the battery is 12 volts. And the voltage across resistor 1 is 8 volts. And IR2, the current through resistor 2, is 4/3 of an amp. Okay, so I might give you this information. Your job is to give me all the missing pieces. What I typically do with these is remind myself, I'll just scribble a little note somewhere saying, okay, IB has to be equal to IR1 has to be equal to IR2. The current's the same in a series circuit. And the voltage across the battery has to equal VR1 plus VR2. Well, all right. I can see that one's going to be easy. If the battery has 12 volts across it and resistor 1 has 8 volts across it, that's telling me that this one has 4. He takes those last 4 volts. All right, so I've got all 3 voltages taken care of. Now, this one's really easy because the current has to be the same everywhere in this circuit. So I got 4/3 of an amp, 4/3 of an amp, and 4/3 of an amp. Not too bad, huh? My last thing to do is to figure out what the resistor 1 is. So what's the value of resistor 1? And at this point you have multiple options for how to solve it. But typically what you're going to need to do is something with Ohm's law. So if we go back to Ohm's law, V equals IR. Now, Ohm's law actually has 2 different forms. The voltage across the battery is the current through the battery times the total resistance, or the voltage across a single resistor is the current through that resistor times that individual resistance. So there's 2 different forms for Ohm's law depending upon if you're talking about the voltage across the battery or the voltage across the individual resistor. This one's pretty straightforward. Most people can get this one really easily. This one is only tricky because of this piece right here. We've got a certain voltage across the battery. We've got a certain amount of current going through the battery. But what's the resistance associated with the battery? What does that mean? And that's where we use the total resistance of the circuit as a whole. So in this case, what is our total? Right there, series circuit, add them up. Okay, so we could say that the voltage across the battery, 12 volts, equals the current 4/3 of an amp times our total. All right, doesn't seem to help, does it? VR1, right there, 8 volts, equals IR1. IR1 is 4/3 of an amp times R1. All right. So here you see 2 different ways to solve your problem. This is going to be much more straightforward. This is easier. So I would just take R1 has to be 8 volts, divide both sides by 4/3, and you would get R1 is 6 ohms. Now we should get the same thing for R1 if we use this equation. So if I do this, our total, I'm running out of room here. Our total is going to be 12 divided by 4/3. 12 times 3 is 36. 36 divided by 4 is 18 divided by 2. Our total is 9 ohms. And our total is R1 plus R2. So 9 ohms must be R1 plus R2, 3. Oh, look at that. R1 is 6. So both ways tell me that resistor 1 is 6 ohms. So I get the same thing both ways. We're all good. I mean, clearly that's faster, but that gets you the same answer. One of the nice things to do is use this to double check. You can double check that, oh, does this all make sense? I have another way to calculate it. If I get the same answer both places, I probably did it right. So for series circuits, this is the kind of process you're going to take. You need to recognize that the current's the same in a series circuit and that the voltage across the battery is going to be the voltage of R1 across resistor 1 plus the voltage across resistor 2. Those two will kind of tell you about this and this. And then you're going to end up using V equals IR, Ohm's law, as well as the rule about resistors in series to make sure that you can get every single piece of information that we need about this circuit. Now we know absolutely everything about the circuit. We know the current everywhere. We know the voltage across everything. And we know all the resistances, and in this case, we even know the total resistance. So that's the basics for series circuits. These are the things you need to remember. Current's the same, voltages add, and your R total, your total resistance, is just adding your two resistors together. So that's series circuits. Now, I might give you a problem where I give you different parts here. Sometimes I'll give you both resistors. Sometimes I won't give you a current. Your job's going to be to just figure out, okay, what can I piece together? What's easy to solve the first step? Usually think about this relationship and this relationship, and then that'll get it to you. All right, so that's series circuits. I'll do parallel circuits next in another video. Good job.